We're here to do our first example with the derivative as a function. I've put some little stars around our definition of the derivative here because that formula is so good to know for this section. So now we'll use that to look at example 1 here. Our function f of x is x squared minus 1, and we are going to find f prime of x. And again, notice how this is different from section 3.1. 3.1, it would have told us to find like f prime of 2 or f prime of -3, something like that. Now there's not a constant in there, it's the variable x, and that's the big difference here. The setup, though, looks pretty darn similar. We're going to write our definition here. Okay, limit as h approaches 0, f of x plus h minus f of x over h. All right, those x's just are plain x's, not x naught anymore. So when we do this, we're still going to use the same type of procedures that we have been. We're going to plug things into our function, starting with x plus h, plug it in right there. Okay. We're going to have limit as h approaches 0. Then we would have x plus h squared minus 1. There's f of x plus h. And then for the minus f of x bit, you literally just write the function over again because that is f of x right there. X squared minus 1. Okay, over h. And now this is going to look kind of familiar. We're going to expand some things out, try to simplify. Just we've got a variable in there of x. Okay. So let's expand that x plus h squared. That would be x squared plus 2xh plus h squared. And then we have our minus 1 hanging on the end there. And let's distribute this negative, minus x squared plus 1, all over h. Okay, we're going to have some cancellation going on here. We've seen that happen before. And so now we've got the limit as h approaches 0 of 2xh plus h squared. And I bet you guys know what to do next. We're going to factor out an h and cancel that out. So take an h out of the top, 2x plus h all over h, and boom, there it is. So that h down in the denominator has canceled out just like we like to see. That's going to help us out a lot here. And we're going to be able to use some direct substitution, just like we've done in the past. Okay. Now, remember to be careful with your variables here because we have x and h, and it's h that's approaching 0, remember? So put your 0 in here, not for x, okay? Just to make sure. So we're going to have 2x plus 0, and that gives us 2x. Okay, so that is the derivative of our function f of x. The derivative, we say, is f prime of x, and it equals 2x. There's our answer. So notice how this really is a new function that we've created based upon the original f of x. It still contains our variable, so we can plug things into this new function just like any other function. All right, it's just a function that is the derivative of f. Now, let's relate this answer that we found here, the derivative, let's relate that to this first idea right here. The fact that the derivative still relates to the slope of the tangent line. This is going to be able to give us the slope of the tangent line at any point. It's just going to be a lot faster than we may have done in the past. And hold on, it's going to get faster yet in the next section. But for right now, this is what we're doing process-wise. But yeah, let's take a look at that by graphing the original function and then graphing the derivative function here. So I'm just going to make a very quick little graph here of our function f of x and then our function f prime of x. Okay, let's set up some axes. Bear with me as we draw this out. We're going to have the parabola and a line to look at here. Okay, so the original f of x was x squared minus 1. That's a standard parabola that's been shifted down 1 unit. So let's put that on here. Here's our vertex, and it opens upward like so. Set up a couple points there. All right, nice little parabola. Okay. I think that point is a little out of line. Let's fix that. There we go. Okay, nice little parabola. And then we want to look at our derivative function. So here's f of x, and then in green, I'll do f prime of x here. And the function is 2x. So that's a line with a slope of 2 that runs through the origin. Okay, so that's gonna look like this. Okay, slope of 2. There we go. All right, so there's f of x and f prime of x. Okay, now let's look at some slopes of tangent lines here. Okay, slope of tangent line to f of x. Okay, let's look at a few different values here. So when x equals, let's say, 0. Okay, so we want to find the slope of the tangent line to our purple parabola there when x equals 0. And let me just draw that tangent line in really quickly. That would be looking at this point right here on the purple parabola. And we want to come in tangent to that point. That would look like this. Okay, which, I mean, my drawing skills notwithstanding, that is a horizontal line. So the slope of that tangent line really should be 0. Okay, so let's see here. When x equals 0, okay, that point right there, f prime of 0, f prime of x, we're plugging in x equals 0 into the derivative. That would be 2 times 0, which equals 0. Okay, so the slope of the tangent line at x equals 0 is 0. All right, m equals 0. M equals 0. This is the tangent line to f of x at x equals 0. And it has a slope of 0, and that's what the value of our derivative function is. So it all plays together. We can see that value of the derivative function here as well. Here's the f prime function. When x equals 0, that's right here. And the value of that green derivative function is 0. Okay, so it all goes together. Let's do another one here. When x equals, let's say 1. Okay, f prime of 1 would be 2 times 1, and that would be 2. Okay, so that's the derivative of our original function f of x when x equals 1. So this really saves you a lot of time as compared to the previous section, because in the previous section in 3.1, we would have had to go in and plug in 2 different x naught values here. First, we would have had to plug in x naught or x sub 0 equals 0. And then we would have gone through the whole calculation, found the derivative value to be 0. And then here we would have had to start over again, plug in x naught or x sub 0 equals 1, go through the whole process, calculate the derivative value. It turns out to be 2. But we don't have to go through that whole process again now. We've taken care of it already up here by finding the general formula for the derivative. So now to calculate derivatives for different points, it's super fast. We can just plug in the value, calculate the derivative, plug in the value, calculate the derivative. It's pretty nice. And we can see how that relates back to our graphs as well. So when x equals 1, that would be this value right here. All right. If we want to look at the tangent line to that point on the purple parabola, the tangent line would look something like this. Okay. Now this is, let me label it, the tangent line to f of x at the point where x equals 1. And notice how we can actually tell the slope of that tangent line because it happens to be parallel to the derivative function. This is just a coincidence here. So here the slope is 2. And that's exactly the value that we're getting from the derivative right here. The slope is 2. Okay. Notice also the value of the green derivative function there. The value of the green derivative function is 2. That gives us the slope of the tangent line. We can see that slope of the tangent line. Everything just plays together so nicely. So, to kind of summarize a couple things here on this graph idea. Okay, where the tangent line is horizontal, that's what we had in this case right here at the bottom of the parabola, at the vertex. Okay, so horizontal tangent line. We got a derivative that equaled 0 because the derivative provides that slope of the tangent line. So m equals 0, f prime of x equals 0. Okay. And then where the tangent lines have positive slopes, that means the derivative's value should be positive, okay? Because remember, the value of the derivative gives you the value of the slope of the tangent line. So that's like we're seeing here in the blue case, tangent line to f of x at x equals 1. We have a positive tangent slope, and the derivative has a positive value. Okay, that's just one example. Another example here of that, let's see, could be like, you know, here at x equals 2, that tangent line would also have a positive slope. In between 0 and 1, the tangent line has a positive slope. Because we can see here that the values for the derivative function are positive. Okay, and then in the opposite case, I'll see if I can squeeze this in here, where the tangent lines have negative slopes. Okay, f prime of x is going to be less than 0. And we don't have an example drawn in right now, but let's look at that. A tangent line with a negative slope would look something like this. Okay, that comes tangent to our parabola at this point right here, and it has a negative slope. Okay. If you look on the green derivative function, you can see that at this x value, the derivative function would be down here somewhere with a negative y value. So negative y value on the derivative function corresponds to a negative tangent slope. Maybe we can see it a little better right here, where x equals -1. Okay, there's the tangent line right there. It has a negative slope, clearly. And our y value for the derivative is also negative. So that's what we're looking at here. It all relates together. Okay. So the value of the derivative tells you the slope of the tangent line at that particular point. That's the main thing to keep in mind.